Let's dive into some details about analog signals themselves and how they're discretized. One of the easiest signals to think of is something we deal with often, audio. In fact, right now you're listening to a recording of my voice where I have a microphone set up, and that microphone picks up my voice and somehow converts it from the analog signal, the pressure variations coming out of my mouth, to an electrical signal that can then somehow go into the computer and be transmitted to your computer or device, whatever you're watching this on, and then to a speaker where your ears can then hear those pressure variations being recreated at a later time. How does all of that work? Because after all, the recording and processing and transmission, all of that is digital, whereas the pressure information is an analog thing, right? It's a continuing variation in the pressure of the air. That's what sound is, right? My voice is generating variations in air pressure. My mouth and tongue are shaping them into words, and you can hear these words. How does that happen? Well, I like the way they've got the microphone oriented in this this picture here, because usually the microphone with this type is a dynamic microphone, which means that there's a piece of, it's about usually inch and a quarter around in a professional microphone, maybe an inch, something like that. Smaller and cheaper microphones typically, but it's a diaphragm. It's kind of like saran wrap, but sort of a harder saran wrap. And what that piece does is as pressure waves hit it from your voice, it literally moves back and forth. So on axis from my voice, it would be moving back and forth towards and away from me. And if you were to plot that in accordance with the way the microphone is oriented here, it's the diaphragm would be moving up and down basically in response to the pressure waves that it is experiencing. Now what happens is there's a voice coil attached to that in a dynamic microphone, and there's other types of microphones that actually make a, can't think of what they're called, they basically have a capacitor instead of, but in a dynamic microphone it basically generates a voltage signal. So that motion is attached to a coil that moves in a magnetic field and generates a very small electrical voltage that can be detected by an analog to digital converter that's in your recording device, in my case my laptop that I'm recording this video on. And what it does is it takes that varying voltage signal and it measures it. It measures the voltage versus time and records those as numbers representing how far away the diaphragm is from neutral. And that's how it actually records the position of the microphone diaphragm over time. And then all you got to do is take those positions and make a speaker move through those positions, and then that speaker will then generate a sound pressure wave that will be a recording of the original waveform. Of course, the analog to digital converter converts that electrical signal. Well, let's start with the microphone. The microphone converts the real analog signal, the pressure variations in the air, to a voltage signal. The analog to digital converter takes that voltage signal, converts it to numbers. Those numbers are stored and transmitted over the internet or whatever method you're using to listen to this video, and then a digital to digital to analog converter on the output side, on your end, takes these numbers that represent the positions the speaker should move through versus time, and sends that out as an analog voltage signal. That's a small voltage signal that goes into an amplifier, and then that amplifier actually drives the speaker, and then the speaker moves the air and causes pressure waves in the air, so it sounds like I'm talking to you, like I'm in the room talking to you. And so you end up hearing that. So there's this conversion that happens from analog to digital, transmission of digital, and of course a lot of processing along the way, and then conversion from digital to analog. So there's an analog to digital converter on the input side anytime you have analog signals coming into a digital machine like a PLC, and then a digital to analog converter on the output side. So all the input modules on PLCs that are analog inputs have analog to digital converters built into them, and all the analog outputs have digital to analog converters built into them. But sound is one of those things you're probably all familiar with. Probably most of you listen to music, and so you could understand what I mean by an analog signal with audio signals. In fact, here's a recording. I believe this is a recording of me saying welcome to MET 284, 382, something, I don't remember. I think it's 382. And what you're seeing here, it looks like just a mess, and maybe you've seen things like this before. This is actually a picture of how the speaker has to move versus time to recreate the sound of my voice saying that. Now, you're not seeing all the details of all the motion. It looks like there's a bunch of thin lines coming off of globs of something green, you know, but actually, if you zoom in on this, you'll begin to see the detail of the waveform. It's just that there's so many times that the speaker moves back and forth, we're kind of looking at the forest instead of the individual trees. So let's zoom in a little bit on the trees. In fact, let's zoom in on this portion, which, if I remember right, is me saying welcome. Okay, so if we zoom in on, this is what it looks like. And by the way, this is in a program called Cool Edit Pro, which is an older program. I haven't bothered to update with a newer version of any audio editing software. If you're interested in editing audio, at the time of this recording, Audacity is a free audio editor where you can go and you can record stuff and look at the waveforms and do all kinds of interesting, fun things. You can make yourself sound like the Chipmunks by changing the pitch, or you can add echo, all sorts of things you can do. Anyway, so this is me saying welcome. And it kind of makes sense, right? The first part of it, there's two syllables there, welcome, right? So it makes sense that there's two separate waveforms where the speaker has to move a lot and then settle down and then move again. And so the first part that you see here on the left is the well part. There's a little bit of a pause where there's not much movement of the speaker. And then there's a part that's filled in with green, right? That's more movement of the speaker. That's faster movement of the speaker back and forth. And that part is the beginning of the come part. And if you listen to that, the come has k at the beginning. It has a k sound. And that k sound is a very high frequency, well, not very high, but higher frequency variation of sound. And so my voice makes the air move back and forth much quicker, or more appropriately, it makes the pressure waves much closer together, the peaks and valleys, the high and low pressure waves much closer together. But let's zoom in on the well part of welcome. If we look at it, now we're beginning to see the path that the speaker has. Now, it's not like the speaker's moving along the horizontal axis. That's the time axis. The vertical axis is the motion of the speaker. Of course, the horizontal axis is, you know, where the speaker needs to be versus time. And so it's kind of interesting. At the beginning, you see sort of a repeating pattern. And that makes sense, the well part, right? Well. I can draw that out for a long time. And you can see the waveform change in its structure and character, but not its fundamental motion as it moves across. Now, I'm not trying to make you an audio engineer or anything. I just want you to see how this works, and audio is probably one of the things you're most familiar with. So how is this done? How is this, you know, obviously it's a recording of pressure variation, and it's the positions that the speaker needs to be at versus time. Of course, the speaker's default position is just the axis right in the middle, that sort of red line. But if we look at this in a little more detail, let's take one of the characteristic variations here. When we zoom in on it, we finally now see the actual samples themselves. You see the data that's recorded is not a continuous line. This line has been interpolated by Cool Edit Pro. And in fact, the data points themselves, those little squares, are the only recording. That's the only thing that the recording actually consists of. And so you can see how it's broken up in time. If you look at the horizontal axis, the axis is in seconds, and so the first number I see is 0.107, the last number is 0.1098. So that's about, what, 0.003 seconds, so about 3 milliseconds worth of data or so. So this whole variation happens in 3 milliseconds, and each one of those samples is a point in time where a measurement of the microphone's position was taken. So the microphone was moving down and then back up for this. It's one complete waveform. Now, hopefully this helps you visually see how the sound pressure or the position of the microphone is being measured at discrete points in time. It's not being measured continuously, right? And that's because of the analog to digital converter. You see the The diaphragm in the microphone is actually moving back and forward continuously, making a continuous analog voltage signal. But that voltage signal, by the time it gets to my computer, is being sampled at unique points in time. In other words, the voltage is being measured at unique points in time, not continuously. Not only that, but the position of the microphone diaphragm, in other words, the voltage, is not measured exactly. It's rounded off to some extent. And you might wonder, well, how rounded off is it? Well, let me go into a quick story. Most of you are probably not old enough to have had a big collection of CDs, okay, audio CDs. Audio CDs came out when I was, teenage years or so, and they were the next great thing. They were definitely much better quality than audio tape or vinyl records, if you know what that is. And so most people switched over to CDs pretty quickly, including me. But one of the specifications you always saw on the front covers when they first came out of CDs was that they were, 44,100 hertz or 44.1 kilohertz and 16-bit. And, well, what did that mean? Well, it turns out that as a human being, you can probably hear about a maximum frequency of about 20,000 hertz, and that's 20,000 high-low pressure points per second. That's a pretty high frequency. If you've ever heard a cymbal, for example, a drum cymbal, or a snare, or the high end of a piano, those things get up into higher frequencies. The low end of the scale, going towards the left-hand side of a piano or a bass guitar, those things go down to low frequencies, or a kick drum, for example, on a drum kit. Those are fairly slow-moving waves back and forth, whereas high frequencies move the speaker back and forth very rapidly. Anyway, your and my ears can't hear all sounds that are possible. Some animals, for example dogs, can hear what's called ultrasonic, frequencies that are above our hearing range. I don't know how far they go. It doesn't matter. The point is that you hear only a certain range of frequencies, and so there's no need to record a sound that's moving back and forth much faster than a human ear can hear if all you're trying to do is record a band playing, because when you play it back, even if the speaker can move back and forth as quickly as the pressure variations in the air were, the human being still will not be able to hear it, so there's no point in having that in the recording. So back to CDs and how they work. They had a left and a right channel, and so there were two separate bit streams representing the right channel and the left channel, since it was stereo. And so the 44,100 hertz, or 44,100 hertz, really was sort of a marketing thing, because actually it was 22,050 hertz for one channel, 22,050 hertz for the other. Now, of course, to sample both, technically the analog to digital converter probably went back and forth and sampled at a rate of 44.1 kilohertz, but that didn't mean the CD-ROM could actually reproduce 44.1 kilohertz unless you did some very special stuff, and that wasn't the norm. So anyway, the point is that still 22,050 measurements of the speaker's position per second is a heck of a lot of data. That's pretty impressive. And then the 16-bit, the 22,050, what did that mean? Well, that basically tells you the resolution in time. So the more samples taken per time, the higher the resolution in time along the horizontal axis here. The more samples we'll have, and the better we can follow the actual speaker's position. But the 16-bit had to do with the resolution in the vertical axis, the amplitude. And so that 16-bit, what did that mean? Well, it meant that each point in time where a measurement was taken was represented with a 16-bit number. Now, if you know anything about binary math, you know that a 16-bit number can represent numbers from 0 to 65535. Just take 2 to the power of 16. If you do that, you'll get 65536 different numbers, but you have to include 0. So it's 0 to 65535. And the way this worked is basically you think about it as very fine steps, from all the way the speaker all the way as low as it can go and all the way as high as it can go. The lowest position being 0, highest position being 65535. The middle position of the speaker, when the speaker is at rest and not moving at all, when the speaker is quiet, would be a position halfway in between, about 32,768 or 32,767. So those two numbers on CD-ROMs told you the resolution in time and the resolution in amplitude. There's something interesting you can do. If you still have a CD, an audio CD, and an audio CD player, you can perform this experiment. Be careful with your ears because you'll have to turn the volume up loud. But if you have an audio CD where the song fades out at the end of the song, this is very common back in the 80s and 90s. The song's playing along, gets into a groove, and that's kind of the end of the song, so they just slowly but surely decrease the volume. If you have a recording like that, near the end of the song, start cranking up the volume to keep the volume more constant. And what you'll hear is the sound will get kind of scratchy. You might wonder why. Of course, take it down very quickly before the next song comes on. You might wonder why that is. Well, if you think about it, the speaker's amplitude is being represented by 0 to 65535. Those are the numbers we have. And as the song volume fades out, what's happening is the speaker is actually moving not so far anymore, because the farther the speaker moves, the louder it will be. So if the overall variation gets quieter and quieter, the speaker won't be moving as far. Well, we're getting into a region where we don't have as many numbers to represent the speaker's position. And so, as you crank up the analog volume on your player or whatever it is, you're actually amplifying something that doesn't have as high resolution. You can actually hear the scratchiness. So it's an experiment you can perform to actually hear a lack of resolution and understand what that would sound like. Why are we talking about audio so much? Well, in an industrial situation where you need to measure some signal or you need to output a signal, you got to decide about your resolution in time and resolution in amplitude. Because if you think about it, say you're measuring the temperature of a furnace, okay? Well, this furnace needs to be heated up, but do furnaces heat up really quick? No. Do they cool down really quick? No. So do you really need to take 22,000 measurements per second like you can with audio? Probably not. If you took a sample or a measurement of the temperature every second, that's probably plenty. Or maybe every minute is fine, right? It just depends on how big the system is and how quickly it can change. As far as measuring the amplitude, what's the analogy there with industrial systems? Well, let's go back to our furnace, for example. There you're measuring temperature, and the question is, how fine a temperature difference do I need to measure? 1 degree Fahrenheit? 2 degrees? 10 degrees Fahrenheit? Well, if you're designing your furnace to operate at, say, 2,000 degrees Fahrenheit or so, probably 1 degree is an adequate resolution. Do you care if it's 2001 versus 2,000 degrees in the furnace? Probably not. Right? That's fine control. So that resolution on the vertical axis does not necessarily have to be 65536 like it is here. 65,000 different temperatures. And the way this works, you might say, well, why would I ever want to measure a temperature up to 65,000 degrees? That's not how resolution works. If you set it up so that your range is from, say, 0 to 2,000 degrees Fahrenheit, you break that range down into 65535 or whatever the resolution is of your system. You break it down into that many steps. So you could sense a temperature change less than a degree in that instance. Okay. Let's take some simple numbers. Let's say you did want to measure from 0 degrees Fahrenheit to 65535 degrees Fahrenheit. I don't know what case you'd ever want to do that or what sensor you would use, but let's just pretend that's the case, and you use a 16-bit analog to digital converter to do it. Well, then each step, each change in the number, each 0 to 1, 1 to 2, etc., would represent 1 degree Fahrenheit. Now let's change it just a little bit and say that, okay, I don't want to measure 0 to 65535 in temperature. That's a heck of a temperature. I want to measure to half of that, which is still a heck of a temperature, but 32,767 degrees Fahrenheit. But I'm going to do it with a 16-bit number still, so I still have from 0 to 65535. Well, now each degree would be 2 number changes. So you can measure down to a resolution of a half a degree Fahrenheit with that. So hopefully that explains a little better resolution. Now, most industrial analog to digital converters don't go to 16-bit resolution. Most of them are either 10 or 12-bit. And you can calculate the resolution in that case. If you have 2 to the power of 10, that's 1023 or 1024. So 0 to 1023 is the range of numbers. And most of the time, that's adequate. I mean, think about it. What if you just wanted to measure a change from a range of temperatures from 0 to 100 degrees Fahrenheit. Well, if you can measure 1,024 different temperatures, you can break that range. Let's make the math easy. Let's say it's 1,000 with 10-bit. You can make that range of 100 degrees divided by 1,000 is 1/10 of a degree you can measure, which is doggone good resolution most of the time for most processes. But in reality, most analog inputs have 12-bit resolution. And so if you take 2 to the 12th, that's 4,096 different levels that can be measured, which again for most industrial processes is completely adequate. I've bought some sensors we're going to play with and some transmitters. One transmitter in particular is for taking in either a RTD measurement, temperature measurement. RTD stands for resistance thermal device, I think. You never can remember. They're expensive. They're usually made out of platinum, so the sensors themselves are $100, whereas the transmitter is pretty inexpensive. Or you can use thermocouples. Thermocouples are cheap. Thermocouples are where you take two dissimilar wires and you either twist them together or you touch them together and weld them together. And because of the dissimilarity in the metal, a small millivolt signal is generated that depends on the temperature at that junction. And so the higher the temperature, the more or less, I don't remember which, but it changes the millivolt signal. And if you have appropriate hardware, you can determine what the temperature is based on the millivolt signal from that junction. And these are really good devices because, number one, they're cheap. Number two, though, you can get a very wide temperature range. So, for example, a Type K thermocouple is particular dissimilar metals that are well known, welded together. You can get it to measure a temperature from 0 to 2,000 degrees Fahrenheit just fine because it's metal. So if you need to measure a flame temperature, you're going to use a thermocouple to do it. Now, we're not going to work with RTDs in this class because I don't have any, but we do have plenty of thermocouples. And the module that I bought, you can hook up the thermocouple to it, and what it'll do is it'll measure the millivolt signal and generate a 4 to 20 milliamp signal, or a voltage signal, 0 to 10 volts, I don't remember which, that the PLC can actually accept as an analog input. And so the way this works, if you buy a transmitter that, look down at the Type K thermocouple section of this table, you notice it goes 0 to 100 degrees all the way down to 0 to 2,000. So if you get a transmitter that transmits 0 to 100 degrees, it doesn't mean that you're going to have awful resolution. It doesn't mean that you've only got 100 different measurement data points. What it means is if, let's say that you've got a 12-bit input card, so 4,096 different levels, well, it means you got 100 degrees divided by 4,096, which is about 0.024. So you could measure a temperature change at the thermocouple junction of about 0.024 degrees Fahrenheit. So you're going to get nice resolution but a low range. On the other end of the spectrum, say 0 to 2,000 degrees, again taking 2 to the 12th as our analog to digital converter, so we've got 4,096 different levels we can measure, and then 2,000 divided by 4096 comes out to almost 0.5, but 0.49 or so. So the smallest temperature change we can measure or detect would be 0.49 degrees. So we're trading off resolution for range in that case, see. The Type K thermocouple is the same in both cases, or as far as we're concerned at this point they are. But the point is this transmitter does the job of converting the thermocouple signal into a signal that the PLC can actually take in on a standard analog input channel. And there's several other devices that I've ordered that we will connect to the PLCs as well. I want to help you understand the idea of resolution, so I'm going to give you an example, a low resolution example that I want you to watch a video for. When I was a kid, I started out with a Commodore 64. That was my first computer. You may or may not have ever heard of them. It had a whole 64 kilobytes of RAM, and now that's not megabytes, that's kilobytes. Today, computers often operate with gigabytes of RAM. So today's computers literally have millions of times the amount of memory that I had in my first computer. And I love the computer. I played games on it. Now these games were, games you can get on your phone are amazing by comparison to the games that I had on my computer. But in this computer, of course, one of the things you needed to have a decent video game is some sound, right? So this computer had what was called a SID chip, SID, a sound interface device, I think. It was basically just a little synthesizer that had 3 voices, and you could make a square wave, triangle wave, or noise, I think, or a sine wave, and make different bleeps and blops and things. Think old school video games with very crude sound. This was not a chip that was made for making a speaker move through a very prescribed waveform so that you could hear my voice. It was for synthesizing very simple sounds. And of course, most programmers used it that way and did their best with it, and you had a simple computer where you could play some simple games on. But some people got a hold of this and they realized, well, wait a second. There's also a 4-bit volume control on the SID chip. So that meant you had 16 different volume levels that you could set the SID chip at. So you can make really quiet sounds or really, much louder sounds. And they realized that if they took this volume control and just ran it up and down real quick, I guess there was a voltage leak or something in the SID chip, I don't know, but the speaker, your speakers that were amplified, would actually follow that along a little bit. And while you couldn't make sound that was as loud as what the synthesizer in it could make with all these square waves and sine waves and so forth, you could still make audible sound, and you could make sampled sound. You could make sound that was, couldn't be very long, it didn't sound very good, but you could make the computer finally talk. It was amazing for the time, back in the 80s. It was just amazing. My computer can talk. That's nothing nowadays, obviously. Now your computer can show you a video from around the world. But back then, just having sampled sound like this was unbelievable. And there were some games that took advantage of this. There was a game I used to play, it was called Beachhead 2. And you'd land, and you had soldiers behind these walls, and you had to tell them to run. You couldn't, I don't remember if you could control the soldier directly or what, but you'd have them hidden behind these doorways, but behind the block wall there, and you'd select one and tell it to run, and the gun down at the bottom would try to shoot your guy. And there was no gore here. It's not like today's games. If your man got shot, it would just stand still and flash color. But the interesting thing about it, I actually liked getting the men shot because they would say, ah, or they scream, or I'm hit, or, and it was just amazing here. Now, it wasn't super high quality sound, but it was just amazing. The computer was talking, which was something you couldn't expect, or wouldn't normally expect. And there was another knife fight at the end. This was another level in the game. I don't remember which person you were. I think the dictator, which was the bad guy, was on the left side, and the allies, the good guys, were on the right. And you had to throw a knife across. Of course, he was throwing knives at you. And I don't remember whatever he said whenever he got hit. Something like, ugh, or, when he threw a knife, he'd say, you'll never defeat me, or whatever. I don't remember. But the point is, it was just neat that you could hear this sampled sound that wasn't just very basic sound. There was another game, I didn't play this one as much, it was called Impossible Mission, and you had to run through hallways and go up and down elevators. Very difficult game. But when you first started the game and loaded it, and I would always load this game just to listen to the introduction, where it was trying to get you to press the fire button to play the game, and there was some music, but then it would stop, and the person, the bad guy, who was, I guess, somebody watching you running around or whatever, would say, stay a while, stay forever, ha ha ha, this very ominous voice, and it was just interesting. So I've got a video where you can actually hear that, and the reason I want you to hear it is not for the sake of my nostalgia, but for you to hear what lower resolution sounds like, so you can begin to understand it. Often low resolution, either discretized in time or in amplitude, is completely acceptable. It just depends on the process and what the process needs in terms of time and amplitude resolution.